Hello and welcome to another session in physics. In this session we'll be looking at the topic electric field. But before that, let us review the previous lesson. Welcome back. Well, let's look at the definition of electric field. We're still on the force fields, and I'll keep reiterating and making it clear over and over again that the field is a region or space under the influence of some physical agency. Physical agencies such as gravity, electricity, magnetism, and electromagnetism. So get that into your head. Now let's talk about electricity or electric field. An electric field, put simply, is a region of space which surrounds a system of electric charges. Put simply, an electric field is a region of space under the influence of electricity. Yes, a region of space under the influence of electricity. You see, electrical forces will act on any electric charge which is placed within this region. When you touch an electrical conductor, a live wire carrying electric current, you are sure to get electrocuted. You will get electrocuted because you are interfering with an electric field. So electrical forces will act on your body to tell you, my friend, you don't belong here. This is not where you should be. So because electric current moves in a specified direction, we say that electric field is a vector quantity. The direction of the field can be determined using a test charge, a small positive charge. Already in previous lessons, we talked about how we can determine if there is the presence of a charge on the body using the contact method, or we can charge a body. We can use friction. We can also use electromagnetic or electrostatic induction, charging the body by induction. We can also use devices such as the gold leaf electroscope to test for the presence of a body and presence of a charge in an electric field. Now we have what we call the fundamental law of electrostatics. This law states that like charges repel, unlike charges attract each other. Similar charges repel and the similar charges attract each other. So negative and positive will attract each other, but positive and positive will repel. Negative and negative will repel each other. Alright, so this principle helped in the formulation of Charles Coulomb's law, which governs electrostatic forces between charges, and this law is known as Coulomb's law. This law aims to describe the electric force that exists between two charges. Now, Coulomb's law states that in a given medium, the force of attraction or repulsion between two charges is directly proportional to the product of the two charges and is inversely proportional to the square of the distance between the two charges. So, the force of attraction between two charges is directly proportional to the product of the two charges and then inversely proportional to the square distance between them, which now results in K1 K, replacing the constant of proportionality all over R squared. Alright, so this is a further explanation of Coulomb's law. We see that this K constant is equal to 1 over 4 pi epsilon with subscripted O. Now this is a Greek alphabet called epsilon. It is not E. It is used to show permittivity, and we'll talk about what permittivity means. Now, relative permittivity of a medium simply refers to the ratio of the permittivity of a medium to that of air. So the relative permittivity of a medium means permittivity of the medium in a vacuum and permittivity of the medium in air. So EM is permittivity of the medium in a vacuum, and permittivity of a medium is given by permittivity of air over that of vacuum. So it gives us relative permittivity of free space. Alright, so let's talk about electric field intensity or electric field strength. The electric field intensity at any point in an electric field refers to the force that is being experienced by a unit positive test charge at that point. Because it has a direction, it is a vector quantity whose system international unit is given as Newton per coulomb. It is Newton per coulomb because it is force over charge. The SI unit of force is Newton and that of charge is coulomb. So mathematically, electric field intensity or strength is given by E equal to F over Q, as you can see from the slide here. Alright, the electric potential this time around, as you can see from the slide, refers to the work done in bringing a unit positive charge from infinity to that point against electrical forces of the field. Let me make it clear that electric forces in a field might seem to resist the bringing of a unit positive charge to any point in a conductor. Hence, work has to be done to overcome the resistances. That work that is done in bringing a unit positive charge from infinity or from zero to any point in the electric field is what we call electric potential or potential difference. It is measured in volts and it is a scalar quantity, and it is given by potential difference equal to work done over the charge, where you can see work done in joules and charge in coulombs. Now this is the formula or equation we can use for calculating electric potential at any point. So at the end of this video, you can quickly go back and go through it again. You remember that this here is our constant K, which shows us the relationship between the permittivity of free space and the distance between the 2 point charges. Now let's talk more about potential difference. Potential difference between any 2 points in an electric field is the work done in taking a unit positive charge from one point to another in the field. There's a big difference between potential difference and electric current, represented by R. Potential difference is the force required to get electrons moving. Of course, you know that no motion can occur without force. For a body to move from one point to another, there must be a force causing it to move. Similarly, for electrons to move from one point in a conductor to another, there has to be a potential difference. This potential difference is the work done in moving these electrons from one point to another. And work done on a charge can be given using this equation. Electron volts is the quantity of energy gained by an electron when it accelerates through a potential difference of 1 volt. At this point, take note of this expression here, 1.6 times 10 raised to the power minus 19 coulombs. This is the value of an electron charge. This is the value of an electron charge. 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joules. This time around it is measured in joules because it refers to energy, but when it is measured in coulombs, it refers to electronic charge. Alright, so an electrical force of attraction is given by this here. You can see from the slide, the E squared, meaning the value of the electronic particle, the electron particle squared, divided by 4 pi epsilon and the square of the radius. The force of attraction means the electrons are moving, hence they possess kinetic energy, which is given as half mv squared. And when you take proportions and just multiply it with this, you can make the electron charge the subject of the formula. Now let's talk about these electric devices known as capacitors. Capacitors are electronic devices that store charges. Their main function is to store charges. They come in the form of 2 conductors which are insulated electrically from their surroundings. Most popularly, we have 2 parallel plate capacitors which are separated by a very small distance. These two plates of the capacitor are made to carry equal but opposite charges, that is, they can carry protons and electrons, positive and negative charges at the same time, and they are connected across the terminals of the battery such that the BD across the plates is V. That way they can retain and store charges. This is a more realistic diagrammatical representation of a capacitor that is being charged. Now look at this diagram very well. You would notice that on one part of the capacitor, on one plate, it is positive. On the other plate, it is minus. When this happens with the dielectric material between them, it means that the capacitor is charging. Because for a capacitor that is charging, one plate has to be positive and the other has to be negative. This is the electrical symbol for a capacitor. Now, let's talk about capacitances. Capacitances simply refers to the ability of a capacitor to retain or store charge. And the charge in a capacitor is given by Q equal to CV, where C is the capacitance and V is the potential difference. Electric capacitance is measured in farads, and most times it is measured in submultiples known as microfarads, or 10 raised to the power minus 6, or picofarad, 10 raised to the power minus 12. A study of multiples and submultiples will help you to understand this better. So micro means 10 raised to the power minus 6, pico means 10 raised to the power minus 12. We also have femto, we have yocto, so I'll give that to you as an assignment and you can go find out what they mean. Alright, so this is the arrangement of capacitors in series and in parallel. Capacitors in series and in parallel. Now, when capacitors are connected in series, their effective capacitance, if for instance they are 3, will be given by 1 over C1 plus 1 over C2 plus 1 over C3. But when they are connected in parallel, they are given as C1 plus C2 plus C3. You would notice that in resistors, the reverse is the case. If we want to find resistors connected in series, it becomes R1 plus R2 plus R3. But for capacitors connected in parallel, this is how they are found. And for capacitors connected in series, this is how they are found. Whereas for resistors connected in series, 1 over R, resistors connected in parallel, we have 1 over R, or 1 over R1 plus 1 over R2 plus 1 over R3. This is for capacitors in series, this is for resistors in parallel. This is for capacitors in parallel, this is for resistors in series. So the opposite of what is done in resistors is what we do in capacitors. The energy stored by a capacitor is measured using any of these three equations. The most popular of them is E equal to half CV squared. But depending on the parameters or the values you have in the question, you can decide to use any of these three equations. Note and remember that energy stored in a capacitor simply refers to the work done in charging that capacitor, and it is measured in joules. For more information, visit the notes attached to this video. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.